Good morning, everyone. This is Mike Dowding from the SD Mines Physics Department. And an apology, I forgot a topic on Chapter 26, which was current density, so I want to go ahead and go back and just touch on that. So this will be a very short video, just so that we can get over that specific topic. But we'll start our discussion with our definition of regular current, which we are using I to represent current. And current, that's going to be the flow of positive charge in a system. Even though we kind of know better nowadays that it's actually electrons that are moving through our wires and all of our electrical systems. There was basically just a generalized definition of current hundreds of years ago when the idea was first brought about. And since then, they just haven't bothered to update any of the expressions, because really all that would mean is instead of having your charged particles flowing in one direction, now they're flowing in the other direction, and that's just the difference in sign notation. And so it doesn't really affect any of the equations that we have in any of our textbooks. It would just flip the sign around. And so what I'm going to go ahead and do, I'm going to stick with the definition of current as being the direction of positive charge flow, but I'm going to refer mainly to magnitude for the rest of our discussions. So with that in mind, because current is the flow of charge, this means that there has to be a source of charge, and typically that's going to be our battery. And then as charge comes out of the battery, it'll go to a resistor or a capacitor or some other circuit element. But since we're talking about resistors in this chapter, we'll go ahead and stick with the idea of the resistor. And then because we have charge flowing out of the battery, that means that there is excuse me, there is a change in charge with respect to time. So charge is moving with respect to time. The rate at which that charge flows, that is what we are calling current. And like in Physics 1, if you remember, anytime we had a large time interval, the best that we could do for our measurement was an average. So this would technically be the definition for average current. If we want to get an instantaneous current, well, then we need to shrink this ratio down to an instant. And we would do that by converting this to a calculus expression. So here we have the two different types of current that we're going to run into. So what about current density? Well, current density is, first of all, current, but then we have the density part of the definition. And if you're like me, back in middle school, the first time you probably heard the definition density, that was mass over volume. And so you're probably thinking, well, I need to take that current and divide it over a volume, but that's actually incorrect, because What we really need to do is we need to know how much current is passing through our conducting material at any given point. And for that, what we do is we look at the cross-sectional area of our conducting material, which, as we know by now, can be represented as a vector. We've used area vectors back in chapter 23 for Gauss's law, and so we can continue using that here. And current density, as it turns out, is actually going to be a vector. And the symbol that we're going to use for current density is a capital J. And so we have the vector notation over the top there. But if our current density is defined as current per cross-sectional area, well, remember that current is made up of charge, and charge is a scalar. Likewise, time is a scalar, and so current has to be a scalar. Now our area, it can be a vector, and in this case we need it to be, but I can't remember the last time I actually had to divide by a vector. And so what we're going to do is slightly rewrite that expression. I'm going to bring the area vector up to the left-hand side so that it's matched up with the current density vector. And then, if you notice, we have the product of two vectors. And you can't just randomly multiply two vectors together. There has to be a specific way of doing that. And that either means using a dot product or a cross product. Now for the dot product, the full name is scalar dot product. For the cross product, the full name is vector cross product. And these two terms out front tell us what the outcome of the product is going to be. And so what we need is a scalar dot product, because we're taking the multiplication of two vectors and we're turning it into a scalar. That means that we can evaluate this expression using magnitude and angle relationship. And this should kind of make sense now, because if I have a current that is traveling through the material in a given direction, or better yet, I should say current density, how does that current density vector match up against the area vector? So think about air flowing through a window. How much airflow are you going to get through a window based on the direction that the air is flowing? So if the air is flowing right through the window, you're going to get a lot of airflow. If the air is flowing in a direction perpendicular to the window, you're not going to get much airflow. And so our dot product relationship right now has a 0 for the angle, and that's going to cause our cosine to go to 1. And now we get to a magnitude expression, which now if I wanted, I could maybe go back to this expression that says current density is current over area. But we have to account for the vector arrangement first before we do that. Okay, so what else can we do with this current density stuff? Because we're saying that current is a scalar, so current doesn't have a direction. Okay, scalars aren't supposed to have directions. If they do, they're vectors. Yet, I just got done drawing a direction of current flow in my circuit diagram. So what is it? Is current supposed to have a direction or not? Well, the way we can get around that idea is to keep in mind that current density, since it is a ratio of current to area, what we can do is we can just kind of fudge the idea that the direction of the current will be the direction of the current density. So we can just kind of borrow the direction of that current density vector and use that to draw the direction of our current. All right, so the next thing we want to consider, whoops, change my pen color here. Now that we have these charges that are moving through our conducting material, so I have some current that's going to bring some charges in. We have all these individual charges throughout the material that are trying to get through, and we need to ask ourselves, well, why are they traveling in that direction? And that's going to be because we're connected up to some kind of potential source. But how fast are these charges going to be moving through that material? And if we disconnect the battery, the first question that I'll pose is, well, without the battery there to provide the potential, will those charges move? And the answer is yes, they will move. This is a conducting material, and just because we haven't connected the battery yet doesn't mean that there aren't any charges in there. But these charges can move around in any random direction that they want. And because of that random direction, if we were to add up the net flow of all the charges, then we would get a current value of 0. It's not until we bring that battery into play that we actually start forcing those charges to start moving in a common direction. So now we'll start to see those charges move to the right. So again, how fast do those charges move through there? And we're going to give that term a name. We're going to call that the drift velocity. And the book uses sort of a italicized V sub D for drift. And we want to know how fast we're moving through there. So the way that we're going to do that, and I'm looking up some of my notes here so that I don't mess anything up along the way. First thing we're going to do is bring in our definition of current. So we have a certain amount of charge per unit time that will be passing through our conducting material. And the conducting material has a certain length associated with it. So there is a certain displacement that the charge has to travel to get from one end of the conductor to the other. And velocity, even though we're looking for a specific type of velocity, velocity is still defined as displacement over time. Well, in our case, we're looking for drift velocity, but how far do these charges have to drift? Well, they have to drift across the length of the conductor, and they have to do that in a certain amount of time, t. So we'll go ahead and use that as a substitution and bring that over to our current expression. So now our current is equal to charge divided by the time. So we have to divide by this expression, and when I divide by a fraction, I have to flip that over. Okay, so now I've got all of that material. But now we need to ask ourselves how much charge was moved through. I made a slight mistake here. I'm going to take a step back. I had one of the wrong terms in there, sorry. What we need to do before we make this substitution is we need to ask ourselves, well, just how much charge is going to make it all the way across that conductor in the amount of time t. So basically what we have to do now is we have to sort of survey this conducting material and add up all of the charges that are present inside that material. And the way that we're going to do that, every material is unique. That's why we have different elements on the periodic table. But every material has its own number of available charge carriers. So remember, the material had a unique resistivity, the material had a unique thermal coefficient or temperature coefficient. Now our materials are going to have a unique number carrier or number charge carrier. Which we will designate little n. So this just tells us how many charges per unit volume are inside that conducting material. And then as we start pushing those charges through, we can start getting a count of how many charges there are. Well, n just tells us how many charges per unit volume. I don't want to know number of charges per unit volume. I just want to know the number of charges. So the number of charges can be found. Let's say number of charges can be found by taking the number charge carrier times the volume. And I think this is why they use that italicized V so that we don't get velocity and volume mixed up. Okay, well, what is the volume of our conducting material? We come back up here. We've done this a couple of times already, but we can get the volume by multiplying the cross-sectional area times the length. So we have our cross-sectional area, A. We have our length, L. That gives us our volume. So the number of charges available now becomes NAL, where the volume was AL. Okay, so this tells us how many charges there are, but it doesn't tell us how much charge. And what we're going to do is we're actually going to consider what's happening in the real world. These charges would actually be electrons in a real world situation. Again, I'm not going to go through and redo everything with the sign notation. I'm just going to go back to the idea that for an electron or a proton, the amount of charge on either of those has a magnitude of E, the elementary charge. And so this is how much charge we have available inside that conductor. That is how much charge that we can move. And that is what we want to do with our current. We want to take our current and we want to move all of that charge over a certain amount of time. Okay, now we can use this substitution because we know that the amount of time that it takes is length over velocity, but right here I have length over time, which is the drift velocity. So now our current is equal to NA drift velocity times the elementary charge. And then we can take that one step further. If I divide each side by the cross-sectional area, if we remember, I over A equals current density J. And if we go back and write current density as a vector, well, that means that some term on the other side has to take on the responsibility of being a vector, and that's going to be our drift velocity. So N was the number of charge carriers, E is the elementary charge, drift velocity, and so now we have our means of describing how fast these charges are going to move through that material. Oops, I can drop the vector notation there if I need to. So we have a magnitude expression here for our drift velocity. So there's the drift velocity. That tells us approximately how fast all of these charges are going to move through this material. And when it comes to electronics, a lot of people have this misconception that electrons are going to move at the speed of light, but that's not true. Really, anything that has mass is not going to be able to achieve the speed of light. We might be able to get something closer to maybe 10% the speed of light in any kind of electronics. But again, this is our expression for the drift velocity that can be found using the current density, the number of charges available inside the conductor is the nail expression there, NALE. And then we had our definition of current and current density. So one last thing that I'll add to this discussion is the idea of conservation of charge / current. There are a lot of conservation laws out there. In Physics 1 we had conservation of energy, there was conservation of momentum. In other courses, you're going to have conservation of charge, conservation of mass, lots of different conservation expressions. And the reason we have all those expressions is because if we're conserving things, then what you have before a given situation has to equal what you have after. And this means that we get to produce a mathematical expression. And once we get the math, then we can actually do some stuff. So what we're going to try here is, as I said, this will be a real quick example here. But we have 3 wires, and they're all connected here at a center point. So I get out some solder and connect them. And then I introduce some current, maybe 10 amps, coming in from the left, and I'll call this current 1. But when that current reaches the intersection, it has to make a decision. Does it go up and to the right or down and to the right? And the answer is yes. It will do both. Some of the original current will travel up and to the right, and some of that current will travel down and to the right. At this intersection, in some classes they would call this a node, but at that node we have to conserve the current that enters and exits that node. So on the left of our equation will be what comes into the node, which was I1. And on the right-hand side of the expression is what leaves the node. And that is going to be a combination of I1 and I2. So let's say we come up here, and we measure the current I2 with a multimeter, and we see that there are 3 amps passing through that top branch. Well, if that's the case, then what is the value of I3? And for the conservation of current, we have to account for 10 amps on both sides, so current 3 is going to be 7. So, like I said, very simple, very straightforward idea. And this idea is actually used in one of the other videos when we talk about equivalent resistors. We have to account for some of the current that's flowing through those circuits, and so this is where this idea becomes important. Well, if that's too boring for you, we can always try a larger circuit where we have a bunch of different currents flowing in and out. We'll say I3, I4, I5, I6. Okay, well, this is quite a bit more complex. So how are we supposed to put together an equation for this? Because there are multiple nodes throughout this circuit, and I can see that, you know, current 3 will come up, current 4 will come up, they'll add together, and they will combine with current 1. But then there's going to be a split. You know, we've got some current 2 leaving there. Whatever doesn't leave through current 2 has a choice of leaving through current 5 or current 6. So here's what we can do. remember that, what we start with before is what we get after. We could take that expression and rewrite it to say something more useful to us, like any current that goes into the circuit is going to have to equal current that comes out of the circuit. And this will make our life way easier, because when it comes to currents that are entering the circuit, trying to change my highlighter color here, there we go. We have I1, I3, and I4 are the current values that are entering the circuit. And that has to equal the current that is leaving the circuit. So I2 is leaving the circuit, I5 and I6 are leaving the circuit. And this would be our conservation of current expression for that diagram. Now, what we do with this expression is, well, that's going to depend on the problem that we're faced with. I would like to have some more information about this circuit, but for right now, I at least have an equation that is describing what's happening in this diagram, and that's a start. Alright, so that brings us to the end of this video. As I promised, it's a shorter video, only about a half an hour. So I'm going to go ahead and close out and post this, and stay tuned for more videos.